All right, folks. So after yesterday's Desmos that you went through, we're going to go through now how to perform the second derivative test to find concavity, the intervals of concavity, and then where on the function itself it changes from concave up to concave down when it does, or vice versa. Okay, so just a little overview of what you looked at yesterday and hopefully figured out from the Desmos activity is when it's up like this, up like a cup, all right? So this little piece of the graph here that you see, all right, that would be concave up, okay? Up like a cup. And then the other part over here is concave down like a frown, okay? As you see me highlighting there, all right? So up is opening up, and down, obviously opening down like a frown, all right? And then you see it in the kittens here too. You got the up, or excuse me, the down kitten, all right, and then the up, opening up here, okay? And then the last thing just to look at on this slide here is sometimes, obviously, a lot of times you're going to have functions where it transitions from one to the other. And what we're going to find today is where does it transition? What is the point at which it goes from down to up or up to down? All right, that is called the point of inflection. All right, and we will talk about that in the next slide. And in this case, it's around about here. All right, whereas this entire part of the graph from going from left to right on the graph is concave down. And then at this point, you see it transition from concave down to concave up, okay? And that part, like I said, is called the point of inflection, all right? So what is a point of inflection? All right, I kind of hit on it before, but just to reiterate, point of inflection is a point where a graph changes from concave up to concave down or opposite, all right? And then the test to figure out concavity, where is it concave up, where is it concave down? Hopefully again, you figured this out yesterday from the Desmos thing, is you're going to use the double derivative, the second derivative to figure that out. All right, so you're going to take a second derivative. We're moving on from the first derivative and doing a second one. And then when you figure out, or when you find out that the second derivative is greater than zero, so positive number, positive second derivative, okay, concave up. Negative second derivative, all right, so less than zero, concave down, okay? And the point between them is the point of inflection. Okay, that is the turning point, all right? And again, just to kind of show it graphically, you got this situation here, concave down, transitioning to concave up, or this situation here, concave up, transitioning to concave down. Where does it happen? It happens there, and that's your point of inflection, okay? So today, we'll talk about how to find that location algebraically. All right, this is concave up, and that's concave down. All right, so you're seeing the transition between the two. All right, again, positive second derivative, concave up, negative second derivative, concave down. Okay, moving on. Okay, so just looking at a function. Okay, so you're looking at this function here, and then just trying to figure out the intervals of concave up and concave down. They are definitely different than the intervals for increasing and decreasing, because in concave up and concave down, part of the concavity, all right, for up or down is increasing and part of it is decreasing, all right? So the points of inflection are different than your critical values that you were finding for the first derivative, okay? The intervals are going to be different too, because on your intervals that you see for concavity, you're going to be figuring out that part of it is increasing, part of it is decreasing, okay, in order to create that either cup or that frown, okay? So in this case, you're looking at an interval from 0 to 4, all right? So we're talking about that being 1, 2, 3, and 4, okay? And over that interval, concavity changes a bunch of different times, okay? And just to kind of go through this relatively quickly so we can get to the algebraic part, you can see that this is from here, from 0 to 1 here, or excuse me, not from 0 to 1, from 0 to halfway between 1, like about here, okay, this here, that's concave down. But then right at this point here, it transfers to concave up, okay? But then back at this point again, you're going to see that it starts to go back to being a frown, okay? So we have down, up, down again, okay? And then this part here from 2 on is completely concave up. All right, so we have a bunch of different intervals of concavity that we would have to identify. Okay, so concave up and concave down. All right, so concave up would be from 1/2, about 1/2 here, to about 1.5. Okay, and then concave, and also from 2 to 4, right? So that would also be concave up. All right, and then concave down, as we indicated before, from 0 to 1/2. All right, and down would also be from 1.5 to 2. All right, and you'll notice too that what we'll do is, real quickly, we'll talk about where it's increasing and decreasing, which is what we got when we did the first derivative, and you'll see that those intervals are going to be different because we are increasing here along this part, okay, and we're increasing here, all right, and then everywhere else is decreasing. So our decreasing goes from 0 to 1, okay, oh, wrong spot, 0 to 1, all right, and then our increasing, okay, goes from 1 to 2, okay, and also from 2 to 4. And you'll notice those intervals are definitely different than the concave up and concave down ones. You'll see that the concave up and down intervals include both increasing and decreasing intervals, okay? So they're different, and that's why we have to use a different trick to find out where those locations are. We have to take that second derivative and figure out how to get those points, okay? Those points in those intervals. So let's go through that process. All right, let's go through a couple examples that show us how to do that process. All right, so I have this function, right? And what you were doing earlier in the week is you were taking the first derivative. All right, you were taking that first derivative, you were setting it equal to 0, you were solving for x. Those were your critical values, and you use those critical values to test and see what side of that critical value is increasing, what side's decreasing, all right? Or are they both increasing or both decreasing? You figured that out by testing points, okay? And then those points gave you intervals of increasing and decreasing and the relative maxes and the relative mins, all right? But for this, we're going to move beyond that step, okay? We're going to do a second derivative, all right? So you could do all the first derivative stuff, and with the practice, you're going to do that, but we're going to skip it for time's sake here and go right to the double derivative, second derivative, all right? And in this case, the second derivative here is 6x minus 6, okay? And that second derivative, we're going to do the same thing. We are going to set that equal to 0 as well, and that is going to be our point of inflection, all right? Solving for that point will give us our point of inflection. So when I solve here, set this equal to 0, okay? And my x is equal to 1 represents my point of inflection. So I'm going to figure out from that point of inflection, what side of that point of inflection is concave up and what side is concave down, all right? So again, I'm doing another number line. This is a second number line now, where that point of inflection, okay, I'm going to test double derivative points, second derivative points on either side of that to figure out what side of that point of inflection is concave up and what side is concave down, all right? So I'm going to start by testing a point to the left. Again, it's all about the sign. So f second derivative of 0 is equal to -6. So that's negative. Remember, negative means concave down. All right. And then I'm going to do the second derivative on the other side. I can just use 2. You can use any point you want. 2 just happens to be a smaller number, easier to figure out the number. All right. And I give that positive 6 is what that ends up being when I plug in the 2 there. All right, so that's obviously positive, and that would be concave up like a cup, okay? And then where does it transition? Right there in the middle at that point, that 1 point, okay? So the way I would, kind of summarize all this information is I'm going to be concave down on the interval -∞ to 1, okay? I'm going to be concave up abbreviate there, CU, from 1 to infinity, all right? And then my point of inflection, again, I'm just going to call that POI instead of writing it out every single time, is at 1 comma something. Remember, x equals 1 is the x part of that. I need the y component of that coordinate. Remember, figuring out the coordinates come from the original function. I have to go back and plug that into the original function to figure out what coordinate this point of inflection happens at. So plug that 1 back into the original. When I plug it in here and here, I get, again, use your calculator for that, -2. Okay? So what we're going to do, I'm going to go over to a graph. We're going to check out the graph and see if that matches. Again, here, this is the graph of that function that we just found the concavity. All right, and we said that our point of inflection happens at 1, -2. So if you look here, there it is. All right, 1, -2. I click on it, it's 1, -2 there. All right, and then to the left of that, so from the reading from left to right, from -infinity to that actual point there, we said it was concave down. Okay, so that matches. And then that transition point there, 1, -2. All right, moving to the right and continuing on that graph gives me concave up like a cup. So that transition point from concave down to concave up, my point of inflection there. So it matches the information that we found when we did it algebraically. Take a look at the second example. We're going to do the same thing. All right, I'm going to have my first derivative and then do my second derivative. All right, and then again, I'm going to set that equal to 0. And solve it. Right? You see there's a lot more on the screen now. So I went through and solved. I got x equals 0 and x equals 2. They're my 2 points of inflection, as you see indicated on the graph there. And then I went through and tested points on either side of 0 and 2, all right, because I had 2 points of inflection there. Had to test on either side of both of them to figure out whether or not it's concave up or down on those intervals. All right, so to the left of 0, I got a negative. All right, between 0 and 2 was a positive. To the right of 2, it was a negative. So I have concave down on the interval from -infinity to 0, as indicated here. Okay, I have concave down again, where the negative is here, from 2 to infinity. Okay, and then concave up happens between those two. All right, from 0 to 2. My points of inflection, so where it changes from concave down to concave up, and then vice versa, all right, are at 0, 0. I got that by plugging the 0 for x into the original function, all right, and then the 2, the other point of inflection, plug that into the original function and you get 16. All right, so this is all the information I need for this. All right, the only other thing I want to do is verify it on the graph and just make sure that what I wrote down there is actually making sense. Here's my graph of that function. Got my points of inflection here at 0 and also 0, 0 and 2, 16 up here. Okay, I got my concave up. Okay, my concave up from 0 to this point of inflection up here, 2, 16. All right, so 0, 0 to 2, 16. Between that, from 0 to 2, concave up as you see there. All right, and then my concave down from -infinity to 0, where it transitions. And also from 216, that point, you don't see the top of it there, but it's transitioning now to a frown or concave down. All right, so what I found algebraically actually matches what's happening on that graph. Number 3, and you can see I kind of went through the entire problem, all right, save some time. So I took the second derivative, all right, passed over the first derivative stuff, doing second derivative, we're talking about concavity, right, set them equal to 0, solved for my x's. In this case, I get a wacky one here, but that's okay, that's what calculators help with, okay? So we use those numbers there. We have plus or minus there, so we end up having 3 points of inflection, 3 times where it changes concavity there, okay? So I put them on my number line, and I'm going to test points on either side of all 3 of those. And you see that I already did that. And I labeled on my graph, where's it going to be minus or concave down? Where's it going to be plus, also known as concave up, okay? And then I marked off those intervals, concave up intervals, as you can see labeled here. Concave down intervals, there's 2 of them as well, right, and they're labeled there. And then what are my points of inflection? Okay, so my points of inflection happen at those x values that I found by setting the second derivative equal to 0. But to get the y part, again, I'm plugging in that value to the original function.